Thank you. Thanks for the introduction. Well, good morning, ladies and gentlemen. I will be the first speaker, evidently, of this morning. Well, basically, it's quite a pleasure to be here in the 5th Young Investigators Conference, and having won the award for the Eccomas. It's quite a privilege indeed. And first of all, I'd like to thank to Dr. Brzezinski and Bizowski for their kind, invitation to give this talk. And today's talk, we will talk mainly about environmental fluid mechanics and building energy demand, and how these quite not related topics have gone together to be formed in a PhD thesis research. And to begin with, I will like to argument, or at least start my argumentation, if this pointer works, of course, yes, regarding the building energy demand. So when I started my master's, which is somewhere here, and when I started my PhD, which is somewhere in between here, we were very convinced that buildings are responsible for approximately 35 to 40, in this case 38 for the case of EU, of the energy demand that's being consumed in the world. And what is really interesting is basically the global share just keeps fluctuating in this range, okay? It doesn't change at all. So basically, we introduced a lot of schemes, energy labeling, building label A, or energy performance directives, LEED accreditation scheme, BREEAM accreditation scheme, maybe one of these things you've heard in the past, and basically in the global share, not a notch happened. So basically that shows that we have still a lot of work to do in terms of building energy demand in the EU, also in the Netherlands. And actually, I like this caricature a lot by Alex a lot, where the climate activist bunny goes to buy a laundry machine and says, what's that button for in the laundry machine? And the salesman says, that's the eco setting. And what does it do? It goes green when you press it, and it gives you a huge sense of well-being. So basically, you don't necessarily get an energy saving, but you get a huge sense of well-being as well. And this basically sums up our complicated relationship with saving the world and reducing building energy demand. Well, if you think about it, and if you take a big picture, the building energy depends on, first, the occupants, so the people. And in fact, if there were no people, there would be no building energy demand as well. So it's quite a linear relationship. Building installations, yes. So the more effective your building installations are, the more, let's say, efficient your water pumps or heat pumps are, then you get lower demand. Then it depends on building envelopes. This is the topic. Everyone talks about insulating the house, changing the orientation of the house, etc., etc. But actually, think about it, there's also the climatic aspect of it. When I was preparing this presentation, my professor told me, if you're going to talk a bunch of engineers and physicists, and if you're talking about scales, tell them what microscale is. So that's why I put this graph. Because he said, for some people, microscale can be something just slightly larger than nanoscale. But no, we are speaking about meteorological microscale, which, according to the American Meteorological Society's glossary, it just means scales that are lower than 2 kilometers. But actually, if you think about it, the climate around the building just occurs in between this range. So you have to be considering a microscale component to have enough information about what's happening around the building. This will be the core, and especially in urban areas, this basically formulates a big deal. Why? Well, first of all, once we know that the installations and the envelopes actually can be modeled, can be designed, they can actually be properly optimized in terms of energy demand, and it may be so much so that you can actually reduce the energy demand before you actually design the building. But we cannot do yet the same for climate. No one actually talks about designing the microclimate around the building so the energy demands will be lower. And this thesis actually was built on this premise. We said, can we model the urban microclimatological aspect? And more importantly, can we somehow influence it to reduce the building energy demand too? Well, the research on urban climates mainly focuses on urban heat islands. Who here have heard urban heat islands before? I'm just checking. Did you hear urban heat islands before? Yeah? So basically, urban heat island is a phenomena that is basically says an urban area which is significantly warmer than its surrounding rural areas. So think of it like an enclosed isotherm where the temperatures go higher and higher, because when you're in the city, the temperatures are high as well. And it's not even a very new phenomenon. So it's not like a 5-year-old, 10-year-old term. The first time it is actually somehow mentioned in a poem is in Roman Empire. The first time it has become a concern is in the 18th century in the United States, when people in cities started to have more heart attacks and people were questioning why. And the first scientific documentation of it is in this book that's called The Climate of London. It's written in 1820 by Luke Howard, and where he did meteorological observations in London. And he is basically an amateur climatologist, so he's actually a pharmacist, but what he did was quite clever. So he had a thermometer set up in the Royal Society. This is Royal Society, Royal Meteorological Society, we call it as well. And he had a summer house in Tottenham, and believe it or not, back then Tottenham was a village and a rural town that was outside of the city. And he kept his temperature measurements here, and his wife kept the temperature measurements in Tottenham. And he wanted to measure what is the difference in between. And after a series of measurements that spans multiple years, he's concluded that the mean temperature in the rural area is strictly about 9.2 degrees. But in the denser parts of the metropolis, the heat is raised by the effect of population and fires to 10.3. So basically, he measured an urban heat island intensity of 1.1 degree. That's averaged over multiple years. So he concludes that London is warmer than London outside or London rural. And basically similar to this measurement, all throughout until 1960s, there were a lot of measurements. So people were like extremely interested in this thing. Why our cities are warmer? And wherever you see a researcher on climatology, they want to do a measurement setup in various parts of Europe as well. Also in North America, by the way. But since we are in Europe, I don't want to mention them. And actually, you can see that the delta T, that's actually called the urban heat island intensity, spans a large variety. It spans almost to 10.1 degrees. That's in London for the year of 1965. So which means there's a big difference between the climate of a countryside and an adjacent urban side. Well, the first things first, people started to empirically predict this. Okay, they went crazy about it. They say, okay, let me just predict what is the urban heat island intensity for a particular city. And there has been so many equations that is needless to mention here. There are a lot of equations that you can use to predict. One of the most popular ones is by Tim Oak, actually in 1973, where he links city size and urban heat island. So what he did was he added a new column next to all these measurements. And he said, well, if these populations are changing in line with the delta T's, maybe there is a logarithmic relationship here. So basically, what he says here is the line corresponds just perfectly well, and then he comes up with this equation, which is nice and fun, but what to do about it? Shall we just remove people from the city to reduce this urban heat island effect? Or shall we make it even more crowded to make it even warmer? So maybe in the wintertime, we will spending less energy. No one actually thought about that, because we didn't yet talk about the physics of it. There were a lot of empirical estimates and no physics into it. And that's actually in an article in 1977 by William Laurie. That's actually, if you ask me, this is one of my favorite articles in my whole research career. Well, actually, Professor Laurie, he's passed away, unfortunately, in a tragic car accident some years later than this. But this has been basically a hammer on the wall of urban climatology, which just shook the entire topic. And what he said was, well, urban heat island intensity depends on so many factors. It is different in daylight and in the nighttime. And it is actually different in summer and winter, in weekday and weekend. It depends on the upwind of a rural area and the downwind of a rural area. And basically, the urban part is also important too. So basically, it is quite useless that we are trying to predict this empirically. And what he said is, there exists a general problem in estimating urban heat islands empirically. That's why we should focus on the physics behind. And when you come to the physics, a topic that we all understand, there are simply 7 reasons of an urban heat island effect, okay? And it ranges from some radiation heat gains, such as the shortwave gain, or amplified long-wave radiation gain due to pollution. You have decreased long-wave radiation loss. You have anthropogenic heat sources. You have also increased heat storage due to the construction materials. less evapotranspiration due to less vegetation, and you have decreased turbulent heat transport. So we have lower winds in cities as well. So we have several reasons. And again, one of the leading climatologists of his time, Tim Oak, came up with the equation that's actually came to be known in his famous article, which is cited more than 3,000 times, I think now. It's actually the energy balance model, where he came up with this equation. On the left side, you see the heat gains. On the right side, you see the heat losses. And that is actually the change that there would be in the urban composition. But there's another problem, and that is the problem of imposing energy balance models in meteorological microscale. So how to obtain building level information? That is quite a difficult thing. You need to be running somehow a lower scale, not a city scale empirical or an energy balance model, but a smaller scale. And you need an explicit coupling of wind flow and temperature field to be able to know what's happening around this building specifically. So basically, if you need to couple wind flow and heat transfer at the same time, you have a very good tool, and that basically is CFD, the computational fluid dynamics. So far, we've seen that we can model urban climates with CFD. This should be possible. And if we can model energy demand with energy simulations, our proposition was, how about combining these two approaches? That's where we stand at the microscale. We will be running CFD for the urban microclimate analysis and energy simulations for analyzing the building energy demand. First things first, what we did was we did a long review. We wanted to basically understand what happened so far in the CFD urban microclimate research. And I was very ambitious back then, and I said, I want to cover all the articles that has ever happened. And then my professor said, you have to calm down. But in the end, we had to go through a lot of articles. And we have created a review of 183 studies from 1998 till 2015. I had to change my glasses for that. And it became to be the first review paper on the topic. That's why it's quite liked by the scientific community. And it has a long list of references, 390 references, which is another reason why people like you in the end as well. What we showed was it is a research topic with increasing popularity. So the graph already shows that. Well, 2015 strangely stands a bit outside of the screen, but it's somewhere here. And two things we showed is that the simulation studies are lacking validation. So approximately 60% of the studies do not consider any comparison with measurements, which is quite interesting. And then there are very rarely links with other scales or other aspects as well, such as energy demand. So no one actually cared about it. Just people wanted to do climate simulation for the sake of climate simulation and to show that they could. Well, in our case, we decided to test our capabilities. So we focused on a city in Rotterdam, a part of Rotterdam, let's say, that is called Bergpolder Zuid, that is in the north of Rotterdam, for those who know Rotterdam. And basically, we wanted to validate our climatic simulations with surface temperature. So what we do with CFD essentially is you create a domain, that is true. You create a high-resolution grid around this domain as well. And then you run a couple of simulations of heat transfer and wind flow by solving the Uran's equations. And in this particular case, we used realizable K-epsilon turbulence model. For those of you who are CFD aficionados, it's because we found out that indeed realizable K-epsilon was slightly better in predicting downflow of the wind near a building compared to the standard K-epsilon as well. And that's why it's the basis of our search as well. For this study, we've used ANSYS Fluent, the commercial CFD solver, but we also have tried many times with OpenFOAM, and it performs equally good as well. And in the end, we get some meteorological data from KNMI, the Royal Dutch Meteorological Institute, for air temperature, wind speed, wind direction, and solar radiation. And these are all hourly average data. And what we did was we ran the simulations, and we compared our measurements, simulation results with measurements from this study of Lucette clock. They had obtained their results from satellite imagery, which was quite, let's say, coarse, but it was quite important because it was specifically focusing on Rotterdam. And they had focused on a specific part of the 2006 European heat wave. And what we did was when we ran the simulations, this was the results. So our simulation results was quite okay in replicating the diurnal variation, but not necessarily in capturing some of the complexities that's occurring. So for instance, if you look at the 18th of July, where the cloud passing over Rotterdam probably have affected the surface temperature readings of the satellite imagery. And in our simulation, we just didn't have it at all. So basically, we have some disadvantages in predicting microclimate as well. Nevertheless, it was actually much lauded because of its being the first CFD or microclimate study to utilize satellite imagery for the sake of validation. And it generally, the paper provides a rough framework on how to run a not so bad microclimate simulation, let's say. And the second thing that we acquired was how important it is to couple wind flow with temperature. Okay, normally energy balance models cannot do that, but what we think is important is to couple wind flow with the temperature field as well. So for instance, have a look at this here. Okay, this is the contours of wind velocity. Red means faster, blue means slower. And here you see that around the building, you see a large velocity gradient. So there's a high velocity occurring in the corner as well. And in the same zone, you get to have a lower air temperature. That's because the air can dissipate much quickly. And vice versa is also correct. So for instance, when you have basically fields of low wind velocity, you get parts with high temperature as well. And this is a level of complexity that you can only get when you are running a coupled simulation, not an energy balance model. While we wanted to carry on, we jumped to another case study that is in Antwerp. This is the Antwerp train station, and this is a park that's called Stadspark. And this entire part is planned to be renovated. And the city wanted us to know, well, what would happen to the park if we want to renovate this part? Should we just maybe take some park out and put them into the urban sphere? And if not, how we can utilize park the better? So we decided to run another CFD study here. So we modeled the Antwerp region using the similar methodology as in the previous study I just talked about. And we decided to predict this time air temperatures because we had measurements. And of course, since air temperature is much more dissipative than surface temperature, it's easier to replicate the absolute values as well. And in this case, we had an average difference of 0.9 degrees throughout a period of 1 month. But what we did here was we wanted to understand how parks cool its environments. And I had so many ideas about how to understand this. And then I found this article from 1990 by Honyo and Takakura. I met with Dr. Honyo after some years actually. And he was an interesting guy. And this paper is actually 4 pages long, okay? It is 4 pages long that includes 9 figures. So imagine the amount of letters that they had, okay? And they're quite interesting, the paper is, because it's so simple to understand. When you read it the first time, I understood it, okay? It's that simple. So I'm sure that it's like a type of a communication that is actually tells you what they want to do and they just show it. So that's why I like this paper a lot. And what they did was, well, we will understand the cooling effect of a park based on 2 parameters. That is the intensity and range of the cooling effect. And they put a park here. Intensity is defined as the maximum temperature drop due to a green area. And the range is the maximum range that cooling effect is actually felt due to the park. And whatever happens, they just communicate all their results based on these 2 parameters, which is very interesting and gave us the idea, well, since we are not doing measurements and since we are doing actually modeling, we have the luxury to consider different cases, to do scenario analysis. So where we had the original case, with the Stadspark, we said, okay, let's remove all the trees in the park and let's put like a main square there, okay, an empty field. And in the third case, let's just model buildings in the locations where there would be normally trees, okay, just in the same locations as trees, but this time with buildings. So we have 3 cases. And you cannot easily do this with a measurement. I mean, you have to have a big excavation team to demolish all the buildings and build them again, etc. So it's not really easy. And with a modeling approach, you can actually do it for some fair reasons. And when we did that, and when we compared the results, we found out that with respect to the prevailing wind direction that's coming from southwest, the park had a maximum cooling effect of 3.4 degrees. That's close to the park, of course. And actually, the range is actually increasing to almost 500 meters. So you could actually feel the cooling almost 500 meters behind the park itself. 500 meters, that is a cooling effect of 0.1 degrees that is actually modeled and acquired according to the results. Well, if we have that much of a cooling effect over such a wide variety of area, this should have an effect on the building energy demand as well. And that's actually what we want to do in the next step. So we looked at the same spot and we said, let's get the meteorological data from a rural station as well, and define 3 microclimatic data, okay? One of them will be in the rural area, so that's outside of Antwerp. One of them will be away from the park, so it's approximately 400 meters away from the park, and the other one will be just in the wake, in the downwind part of the park as well. That's called urban number 2. And the microclimate data is produced for 1 month of CFD simulations that require approximately 500,000 iterations, and we had to use a supercomputer to basically make it run. And then we actually would run a building energy simulation focusing on a single type of building that has the same form and same orientation, but different construction characteristics and different use types. So residential office or 6 type of construction characteristics. This is a very outdated building typology, and we even considered the newest low energy guidelines or post-2005 design guidelines in Belgium as well. So it's quite a varied sense. And the first things first, what we noticed was the effect of our microclimate on the energy demand itself. So we are comparing the rural building with the urban buildings, okay? And we found out that the max change for a same construction type ranges to 108%. But actually, if you're looking at it, the averages actually are, or at least the differences are getting lower and lower. That's true. But for the older buildings, actually the cooling demand is still almost 1-to-2 ratio for a building that's in the countryside and in the city center. Moving on, what we also found was if you're looking at the effect of the park itself, you have approximately 14% less monthly cooling demand in the building close to the park. So basically, if you have a same building, same dimensions, same building type, and same construction characteristics, you would have 14% less cooling demand if you are living close to a park. And none of the previous building energy guidelines or design guidelines actually take into account this kind of differentiators. What is even more interesting is that if you look at the daily cooling demand, then you can actually reach up to 40% of differences as well. And this is a chart that I actually like to speculate a lot, that because it takes too much time to describe what's going on here. The arrows show the daily dominant wind direction for particular days that we've done this modeling work. And this one, for instance, indicates that it's coming from the quadrant 3rd, and the red one indicates it's coming from quadrant 2. The black one shows that it's coming from quadrant 4, and the green one shows that it's coming from quadrant 1. So basically, if the wind is coming from south wind towards this direction, basically, since this point will be in the wake of the park, it has up to 40% less cooling demand, because it can utilize the cooling effect of the park much more compared to the other building, which is very far away from the building. But when it's coming from a very irrelevant direction, such as from northeast, then the differences actually are quite negligible, and the cooling demands occur more or less the same. Basically, not only the presence of a park affects your cooling demand, but even the meteorological wind direction affects your cooling demand too. And the last one that actually I like speculating also a lot is which buildings are more vulnerable to urban microclimates considering cooling demands. Well, this actually started from another research that I read some years ago that shows the global residential energy demand, okay? And they expect somewhere within the 21st century, that's most likely 2065 or so, the cooling demand of the buildings in the world will surpass the heating demands of the buildings as well. So basically, the low energy buildings that you are designing today, bearing in mind putting a lot of insulation and a lot of air tightness into it, and with high insulation factors, these low energy buildings might not still be a low energy building in 50 years time, because we will be speaking about an entirely different climate. And this complexity is not in any of the building design guidelines so far. And if you look at our results, you see something similar as well. So for instance, if you look at let's say an urban building that is actually designed in pre-1946 conditions, you would get this much of cooling demand. That's fine. And when you make it low energy, you basically have almost 1.5 times increase. So basically, if this cooling demand keep increasing, then at some point, this will go even higher, but this will go much higher than that. So basically, you are actually kind of pushing a very difficult situation for buildings to overcome in the future period as well. Well, to conclude, I would like to do some key achievements based on what our research has actually led to. Well, the first one actually I want to talk about is we have written the first review paper on CFD or microclimate analysis, and we are really proud of this work. It has been now quite well cited too, but also we get really good reactions to it as well, because we really try to show some past achievements and provide some future perspectives as well. Indeed, it was the first study that we've done the validation of Urban microclimate simulations with satellite imagery data. And the next achievement that we had was the park cooling effect. We had actually studied it, and this became the first detailed study on range of the park cooling effect too. We had actually quite a harsh time with our reviewer to get this paper published, because the conclusions that we reached with him on the same paper was totally different. Then we also had to incorporate some of his conclusions too, because they were really, really valuable. That's why I like this paper. It became really like an international work. And indeed, in our case, the park investigated had a maximum park cooling effect with an intensity of 3.4 degrees and a range of approximately 500 meters. And the last one is actually the most interesting one in terms of achievement. Was indeed we had shown that cooling demand differences can be substantial for buildings in cities and in rural areas. But this has led to saying that engineers and designers should stop ignoring the effect of urban microclimate in their calculations and in their simulations of energy demand. And in turn, this has led to the fact that we actually have now, we are now incorporating, in Belgium at least, different energy efficient building guidelines for buildings located in cities and in rural areas, so that they actually start to take into account that the urban climatology is an indispensable aspect for their energy in built environments. And I would like to conclude, since this is a young investigator conference, I would expect young researchers here as well. I started my research career centuries ago in Istanbul as a bachelor student. And back then, actually, for me, literature research was only a homework to do. And I really hated it. We were only doing it to get some answers to our questions. We would just read whatever we were told to do. And over the time, I started to actually enjoy it more and more. And in fact, I think this thesis is actually a sample of that as well. I have literally learned a lot of stuff reading a lot of antique materials from 19th century or even 20th century. Articles that are rotten in dust, but there are a lot of things to be read there to formulate your next question and to satiate your curiosity. That's why I think I agree with Sir Isaac Newton here. If I've seen further, it is by standing on the shoulders of giants. And with that, I would like to basically thank to some particulars here to two wonderful institutions who have actually co-funded my research. These are the primary giants of my PhD journey, so my supervisors, who have really helped me shape my future as well. Certainly friends, family, and my girlfriend, who is here as well today with us. And last but not least, for the award, I would like to thank all Eccomas community and the award committee as well. And also to the organizers of the Young Investigator Conference, in particular to Dr. Brzezinski and Dr. Buzowski for their great help. And I'm happy to have some questions.